All right, let's get started. Welcome to the group-based crypto session. And we have 4 talks in this session. So we'll start off by hearing about how to build verifiable delay functions from Luca sequences. The work is by Charlotte Hoffman, Pavel Hubacek, Chetan Kamath, Tomasz Kerniak, and Tomasz will give the talk.
Hello, everybody. In this speech, I will introduce verifiable delay functions and Luca sequences, and then we will put it together and we will discuss sequentiality and verifiability of our VDF candidate. So verifiable delay function is a function parameterized by some t, and we require it to have 2 properties. First of them is sequentiality, which means that evaluation of ft requires t sequential steps, and this computation cannot be speeded up even when some parallelism is available. And usually we reach this property by taking some atomic function f. You can think about f like it can be a hash function, and we compose it f times, t times. And the second property is public verifiability, which means that there exists an efficient algorithm P such that P on input X and T evaluates the function, and at the same time, it produces a proof pi for a relation ftx equals y. Verifiable delay functions have many applications. We can build resource-efficient blockchains from them, random beacons, short-lived crypto primitives, proof of data replications, and many others. Despite the fact we have so many applications, there are not so many practical constructions. The most practical ones are from Piecak and Veselovsky, and they are based on hidden order groups like RSA group or a class group of quadratic residues. And we have other candidates based on snarks. We have some based on isogenies, some candidates based on squaring in finite fields. And very recently, we have some first quantum resistant candidates based on lattices from Malavota et al. So we were searching for another source of sequentiality, and we come up with this idea of taking Luca sequences as a base for the construction. So what Luca sequences are, we have 2 of them. It's a sequence U and V parameterized by some Q and P. And these are linear recurrent sequences of order 2. They are generalization of many other well-known integer sequences like Fibonacci numbers or Pell numbers. And they have found many applications in number theory, namely we have some primality tests and factorization algorithms based on them. And also there were some attempts to build crypto systems based on Luca sequences, but these were not shown to have any significant advantages over the state-of-the-art solution. So how to put it together? Our construction is pretty straightforward. Function GT takes parameters P and Q, and it produces 2 to the thief members of the sequence U and sequence V. It's a well-known fact that we have closed formulae for recurrent linear sequences. In this case, we are taking roots of the characteristic polynomial of a sequence, and we are able to express nth member of sequence U and V by nth power of these 2 roots. It's a root and its complement. And I want to emphasize in this place that these roots, they belong to some extension field, namely we extend group Zn by square root of discriminant of the characteristic polynomial. And this simplifies our notion extremely, and it also simplifies reasoning about our PDF. So let's discuss the sequentiality. Here, I would like to refer to the delay function which was introduced by Rivest Shamir Wagner in 1906. You cannot really prove sequentiality. You have to introduce some hardness assumption, and that's exactly what they did in their paper. They stated that this iterated modular squaring is sequential. They do it implicitly in the paper. We would like to get a similar claim for our VDF. And here we have a positive result of our work because we are able to reduce sequentiality of Lucas verifiable delay function to the sequentiality of RSW function. And I would like to show you the reduction now because it's not that difficult. So we have some identity for Lucas sequences, which allows us to compute 2 to the t power of the parameter q whenever we have computed 2 to the t members of Lucas sequences u and v. We can use it for the reduction in this way. So we are given some algorithm which computes Lucas sequences, and we are given some x. We set q to be equal to x, and we pick a random p. We compute Lucas sequences u and v. We plug in the result into the identity, and in the end, we will get appropriate power of x. And naturally, we have tried to do reduction in the other way, and we haven't found any. And we have some evidence why this is not possible. Namely, for example, we use RSA group only. We don't use only multiplicative group of RSA, but we use full arithmetic of the RSA ring. And we have conjectured that there probably will be some sequentiality gap between RSW function and the delay function based on Lucas sequences, which is good news, because if this is true, then, for example, if a new algorithm for computing modular iterated squaring in RSA group will emerge in the future, it will not necessarily affect security of our construction. And finally, let's discuss the verifiability. Here we adapted Pietazak's protocol, which is a folding protocol. It works in a way that in the beginning, we are given some instance, x maps to y in t sequential steps. And we take some midpoint of this function, midpoint mu, to split this instance into 2 instances of half size. And then a verifier picks some randomness, and we merge these 2 half size instances into 1 half size instance. And this goes on and on until we finally, after log t steps, reach instance of size 1, which is easily verifiable by squaring x and comparing with y. So let me sum up which modifications we had to do, comparing Pietazak's work with our work. So we use a different base group. We use the same function, but over a different group. And we had to be real careful about choice of the factors of our moduli, because for the soundness of the protocol, we need to avoid all groups of small order or all subgroups of small order. And in Pietazak's case, this is easily doable by choosing safe primes. In our case, we need to satisfy additional condition, and that is that also ZP plus 1 taken as multiplicative group doesn't have any subgroups of small order. And we have shown in the work some algorithms how to sample these strong primes. We have also tested this, like really generating some examples of them. And the only problem with strong primes is that there always must be some cofactor by the construction. So in Pietazak's case, there is a cofactor 2. In our case, there will be some small constant a as a cofactor, which has to be cleared before we get a group without subgroups of small order. And this causes another trouble, namely we need group membership verifiability, which is quite easy in Piazak case, because in Piazak case, for verifiability, it's enough to take a square root of the element which is sent by prover, and the square root is easily obtained as a previous member of a sequence, while in our case, we need eighth root of a midpoint, which is not easily computable in RSA group, but we came with some trick how to do this by delaying cofactor clearing. So let me sum it up and mention some open problems. We have proposed a new VDF candidate based on new hardness assumption. And we have proven that this hardness assumption is actually reducible to the well-known hardness assumption. And also, we have described some generalization of the Piazak's protocol. And we have stated this conjecture about sequentiality gap between the delay function given by Rivas-Chelmy Wagner and a delay function based on Lucas sequences. And the very important, very interesting open problem I would like to mention in the end of this talk is that actually we were in the beginning of this work very interested into different type of moduli. We were interested into Mersenne number moduli, because if we were able to get verifiability for Mersenne prime moduli, then we were able to certify primality or like at the end non-primality of Mersenne numbers. These Mersenne numbers are the biggest prime the humankind knows. You can see an example in the slide. And there is a whole community who are trying to compute them, and it would be very helpful if they had some verifiability, something like more straightforward than just cross-checking computation, which was done by somebody else. And here my colleagues have the first small steps toward this goal, and that's certification of prof numbers, prof and prof primes, or in their case, they are able to certificate non-primality of these. You can see an example of prof prime in the slide. That's all I wanted to tell you. Thank you for your attention. I open the space for questions.
Any questions? I have a quick one. So are you able to adapt your constructions to have other like VDF properties like uniqueness or tightness?
I don't see straightforward approach how to get uniqueness because of this cofactor clearing, which is different. And I don't know what the tightness is.
Oh, tightness is where if you're given the proof, you're not able to compute the VDF any faster.
Oh, I'm not sure about it.
Okay. Yeah.
Right now.
Thank you. Let's thank the speakers again.
Thank you.
All right. Next up, we'll be hearing about limits in the improvable security of ECDSA signatures by Dominique Hartmann and Aika Kiltz, and Dominique will give the talk.
Okay, thanks for the introduction. Yeah, I'm going to talk about the limits in the provable security of ECDSA signatures. This is joint work with my advisor, Eike Kills. And so, first of all, why would we even still bother with ECDSA signatures? Well, mostly because they are just ubiquitous. You see them in TLS, in blockchains, in JSON Web Tokens, basically everywhere. However, despite the ubiquity, there's still comparatively few security results on them. And all of them require some very strong idealizations like random oracles or similar. So this is often a very uncomfortable situation, and we would like to have standard model results. So let's look at ECDSA and see why this is necessary. Or rather, we won't look at ECDSA specifically, but at GenDSA, which is a generalization, where we just say we use a group and not a specific one, which makes our results a bit more general. So the key generation is very simple. We sample an exponent. This is our secret key, and G to this secret key to our secret key is our verification key. And to sign a message, we first start with basically the same. We again sample a random group element, big R, and we hash our message. And now comes in the weird part of ECDSA. It's this conversion function f, which takes a group element and maps it to an exponent. However, this has nothing to do with the discrete logarithm, and I'll get more into details on this later. For now, just believe me, you can efficiently compute this function f, and it is important. As a last part, we compute this value s, which basically combines all the previous values we computed. And if t and s are non-zero, then they form our signatures. Our signature, otherwise we'll have to try again. Verification also checks that t and s are non-zero, and we recompute the hash and check this complicated looking equation, which basically just recomputes the big R from signing and checks that f of this recomputed value is actually the same as the t we received as a signature. So let's look more at this conversion function. It was pointed out rather early that this is very important to the security of ECDSA. However, in practice, this function is very simple. Namely, for DSA, where our group is just a prime order subgroup of a finite field, we just take the group element, look at the bit representation, see this as an integer, and reduce it modulo p, and that's the output. And for ECDSA, it's not more complicated. We take the x-coordinate of our curve point and again reduce its bit representation as an integer modulo p. So the upside of this function is that it completely breaks algebraic meaning, because like this resulting number has nothing to do with the group element, except that it basically shares almost the complete bit representation, but it has no connection to like its discrete logarithm or anything. However, on the other hand, it has nothing like unpredictability, which I don't define. It's just, it is not random at all. You don't introduce any randomness. It's not like a hash function that is supposed to look random. It's basically just, we throw away some bits by reducing modulo p, and that's it. So where's the problem? Well, the problem is, it was shown rather early that it is unlikely that we can find a standard model proof for ECDSA, or GenDSA, so we have to idealize. And there are three parts which we could look at. And the first one is, of course, the hash function, which we could model as a random oracle. This was done by Verschadal in 2017, but they don't get full security. So that's unfortunate. And actually, it turns out in this work that their limitation is inherent. So we could also idealize the group as a generic group, which was done by Groth and Schub, but this is an even stronger idealization than the random oracle model, so we would also like to avoid this. So what we look at is the conversion function, which also by Verschadal in the different paper was idealized as a so-called programmable bijective random oracle, which is basically a random bijection. And we will look more into this. And for that, let's look at how they actually model this conversion function. Namely, they don't model the complete function as an idealized object, but they split it into three smaller functions. Namely, this phi, pi, and psi. And they all have one part to play in this reduction or in this structure that I told you about. Namely, if we again look at the example of ECDSA, this psi in the beginning maps a group curve point to its x-coordinate, or rather the bit representation. The pi in the middle performs this reinterpretation as an integer, and the psi is the reduction modulo p. So we have these three components, and we only idealize the one in the middle. And we now model this as a bijective random oracle, so as a random bijection where everyone has oracle access to a forward and backwards oracle. However, I just told you that this pi in the middle basically just reinterprets a bit string as a number. So basically, it doesn't really do anything. It doesn't change bit representation. But now in the proof, we suddenly have to model this as a perfectly random function. This is somewhat unrealistic. And so we asked ourselves the question, is it necessary? Or can we do with something weaker, which is hopefully more realistic? And for that, we looked at the previous results by Verschadal, which show that from the discrete logarithm assumption, we get U of NMA security if we model F as a programmable bijective random oracle and also use rewinding. And we also get full UFCMA security from NMA security, again, if we allow F to be a programmable bijective random oracle in the sense that I showed you before. We contrast this with impossibility results, namely we show if we remove even one of these properties, then suddenly we can't get a proof in. And as an additional result, we also show that the generic loss of a linear loss in the number of users for multi-user security, showed by Galbraith et al., is also apparently inherent for ECDSA. So let me give you an intuition on how we arrive at these results. And for that, first, let's talk about how we get security in the first place. Usually, we do this by a reduction. And for such a reduction, we assume that there exists an adversary and show if we have such an adversary, we can build a reduction that breaks some hard problem. But now we want to show that there can't be a reduction, so we just treat the reduction as our adversary, and we do this in a so-called meta-reduction. So now we assume that we have this reduction in the middle, which simulates everything it has to do for an assumed adversary. And but now we assume that this reduction exists. So we, as the meta-reduction, now want to use it in the same way we usually use an adversary as a reduction to break some hard problem P prime. So in order to do this, we now have to simulate an adversary as well as the problem that R is supposed to break. And notice here that this oracle O that the reduction simulates for the adversary is internal to the reduction because it's a programmable oracle. The reduction has full control over it and can just do with it whatever it wants. On the other hand, if we look at this oracle as a non-programmable oracle, then it is external to the reduction, so the meta-reduction has to simulate it, which can actually be quite helpful in our proofs. Now, the problem is we now have to simulate an adversary against ECDSA, for which we don't, it's not broken or anything, at least not as far as we know. So we have to simulate such an adversary that is successful, but we don't have the secret key because the reduction just gives us a public key and we have to work with it somehow. So how can we get around this? We do this by using an assumption that the meta-reduction detects. Namely, we reduce our meta-reduction will break the so-called freebase one more discrete logarithm assumption, which is a slight variant of the maybe more well-known one more discrete logarithm assumption, where in addition to a discrete logarithm challenge, our meta-reduction gets two oracles, namely a discrete logarithm oracle and a challenge oracle. The discrete logarithm oracle basically breaks the discrete logarithm assumption for us, but we can only use it if we query more challenges. So for each additional discrete logarithm challenge that we have to break, we get one query to this oracle. But this oracle is very convenient because it essentially breaks ECDSA for us immediately. But now we have a second problem. We want to use it, so we need more challenges. So how can we extract the solution to all these new challenges that we will need for simulation? Well, for that, we have to introduce the algebraic group model. So in the end, we show that there can be no algebraic reduction that actually breaks, reduces the security of ECDSA. And also, we use some clever simulation of the non-programmable bijective random oracle, because now in our case, since we in many of our examples assume that it is non-programmable, it is external to the reduction, so our meta-reduction now has full control over it. So maybe let me conclude with some interpretation. Maybe the important question is ECDSA now broken? No, it is not. But we've shown that the proofs require some very strong and potentially unrealistic idealizations, since this modeling of this conversion function using a programmable bijective random oracle is somewhat questionable. Secondly, we use this weird freebase one more discrete logarithm assumption, and this sounds very strong. And often we want to avoid strong assumptions. And of course, this is true here as well, but we only use it for meta reduction. So even if it were to turn out false, then at least we don't lose security and suddenly our data is breached. We only lose the impossibility result, which is unfortunate, but also doesn't hurt anyone. In a sense, it's a win-win situation. Either we break some assumption, or we know lots of information about ECDSA. Finally, can we get around our impossibility results? Yes, in some sense we can, because as I said, we only rule out non-algebraic algebraic reductions and black box reductions. So if someone comes up with a non-algebraic or non-black box reduction that can get around it. And also we only show that we can't get security from the discrete logarithm assumption. However, all known reductions that are not in the GGM in the end use D-log. So this is also basically applies to all known reduction that we have. That's it for my part. You can find the full version on ePrint, and I'm glad to take questions.
Thank you. Any questions? I have a quick question. Can you elaborate a little bit on the intuition behind how you do the simulation of the oracles in the second step?
Mostly we just do lazy sampling for the most part. The only part where we actually, in a sense, program the oracle is that when we choose group elements for the inverse queries, we choose them in such a way that we know the discrete logarithms, similar to what the AGM gives us for group elements that the reduction outputs anyway, because in the end we will need that to solve the equations to get all the D-logs for our meta reduction.
I see. Thank you. All right, let's thank the speaker again. And yeah. The next talk is on why round robin is optimal for group action-based protocols. It is by Daniele Cozzo, Emmanuel Giunta, and Emmanuel will give the talk.
Hi. Okay. So thanks for the introduction. So today I'm going to talk about round robin protocol and group actions. So let me first define what are group actions. So a group action is a binary operation between a group and a set that is distributed with respect to the operation in the group and is supposedly hard to invert. We are all familiar with examples of group actions, one being, for instance, the scalar multiplication in prime order groups. Although that is not post-quantum secure, of course, it's the Dirac problem. And we study group actions because they are supposed to give rise to post-quantum hard problems. We also have some concrete instantiation, but the issue is that in the general case, where the set has no group structure, they have, of course, less structure. So it's hard to come up with construction in this setting. So the problem I will be focused on today is essentially the following. We have n parties with a secret share S, with a secret S shared among them. And they want to reconstruct the action of this secret applied to some given set element. You can think of this as some kind of like reconstruction in the exponent. And this problem is fundamental for many primitives, including distributed key generation or thresholdizing encryption scheme or signature scheme in the setting of group actions. So as a warm-up, let's first see how easy it is to do this in the group setting. In the group setting, if we have, for instance, an additive secret sharing of S being an integer modulo P or modulo Q, every user can simply exponentiate or take a scalar multiplication of the generator times their own share, broadcast the results. Then you can just take all these group elements, add them together, and you get the result. You get S multiplied by G. So this clearly only requires 2 rounds. It's very efficient. Everybody only perform 1 scalar multiplication. So it's extremely efficient. But it strongly relies on the fact that we have an operation on the group, like we have an addition on the group. So the moment we lose this addition on the group, so we don't have an extra structure anymore, things get more complicated. And in particular, one of the best protocol we know in the setting of group action is just a round robin protocol. That is, the first user exponentiates or applies his own secret to the first set element, get the results, and pass this result to the next user. The next user does the same, exponentiates the set element it received by his own secret and pass this to the next player, and so on. So this protocol, in terms of computational efficiency, is as efficient as the one I presented before, but it requires n rounds of communication, which may not scale as nicely as before. And also present another small issue, that is that only the last user eventually get the result, which means that if the last user decides not to share this result to the others, then we may either have to abort the protocol or have some way to recover this from these kind of issues. So I will first focus on the second issue because this was actually solved or at least addressed in a previous paper by Lefebvre and Meyer in 2020, where essentially they observed that it's possible to just execute n times a round-robin protocol. So each time we have we order user in a different order, in such a way that every user is the last one in at least one of those execution. And while this is actually very expensive because we require n squared computation, it is also possible to do things a little bit more in a smarter way, batch some of these execution and eventually get communication complexity to and computation complexity to n log n. So the question we ask essentially are if the round complexity or round robin and this communication complexity are optimal, or if there is something we can do to improve them. And before I state our result, let me first spend a few minutes on the model in which we prove our result. That is the generic action model, which was introduced by Duan Hartmann and Kiltz and other people from Bochum. And essentially, the idea is just generalizing the Shoup group model, essentially the GGM, but in the context of group actions. So in this case, set elements are labeled by a random labeling function, this sigma. And there is no circuit that allows the user to compute the group action, but instead the action is performed by an oracle that simply takes one group element, the representation of one set element, and returns the representation of the action applied to this set element. There is a minor note I need to make that we slightly deviate from their model, as we do not include extra oracle for some operations that are possible in the specific context of C-side. We don't in particular include an oracle for quadratic twist, but instead we encode this extra operation in the group and generalize a little bit how can this group be. So we assume that the action is not faithful and the group doesn't need to be commutative. Okay, so that was a minor detail. So now we can finally state the result. So the result is that in the generic action model, that is for essentially adversary that or users that use the action in a black box way, and whenever we have a T out of n secret, secret S, T out of n secret shared among n user, so there is no way to compute the action of S on E in less than T rounds, unless the protocol is insecure. And the second result is essentially that any T-round protocol in which T user computes the output in the second to last step cannot require communication complexity smaller than T log T. So essentially that the previous construction by the Lefebvre Meyer is optimal. So of course, some consequence of these results. So the way to interpret this is essentially that there are two ways of building protocols from group actions. So one is essentially using the action as a black box and therefore falling in our impossibility results and using any T-round protocols. And the best one is, of course, the round robin because it's computationally efficient. Or the other way is just not using the action in a black box way and using a circuit that evaluates the action. And this is possible. I mean, whenever we have a circuit, then we can reduce the round complexity by running generic MPC, like linear secret sharing based, or even garbled circuits for constant round complexity. But on the other side, this is very inefficient because this action has the circuit representing this action is significantly complex. So now, having stated the results, I would like to give an overview of like how do we get at least the first result. So what are the techniques we used? And before presenting that, I would like first to show how computation in the generic action model look like. So to do so, we study the following setting. So we suppose we have one user who has one set elements. And what he can do is like, first, he chooses one group element S, and then he has to compute the action of S applied on E0. So how can he possibly do that? So we assume that this user is making several queries to the oracle that is computing the action. So during its execution is going to see several set elements. And all these set elements, I mean, at this moment appear to be quite random, but in fact, we can define a natural relation among these elements. That is, we can say that one set elements yields the next one. If, for instance, D is used to compute E in this case, and the second one was observed before the first one. So given this relation, observe that, of course, the second condition is imposed to avoid cyclics in the graph. And given the first one, you also observe that any edge in the graph is also I mean, to every edge, we can associate the group element A that was used to compute E from D. And the idea is that what you can show is that in this setting, with this notation, the output must always be connected with the input, essentially. So I cannot come up with the output out of thin air. I must always compute the output sequentially applying the action to the first element. So this is the idea. So now we can move to the interactive setting. So now we have several parties who wants to compute the action of S applied on E0. And as before, they're gonna use the group action oracle to compute several set elements. And again, as before, we can define some relations among these set elements defined by the action, the way the action is computed. So the idea is that we want to show that for any R round protocol that computes the correct output, there must be some path that goes through exactly R users, or at least at most R users, from E0 to the output. Now, this in general need not to be the case. There can be certain cases in which there are paths that goes through many users, although it's somehow weird, because in the same round, users are not allowed to communicate, of course, by definition of round. But what we show, and that's the important thing, is that it's always possible to find at least one path that goes through at most R users. And this allows us to conclude our first results. And the idea is basically that if we have any T-1 round protocol that securely computes, supposedly secure computes the outputs, we can find such path, and then we can use the group element used by this user to compute the output. Summing all these elements together eventually allows this T-1 user to recompute the secret, which breaks security. So that's it, and I would like to thank you for the attention.
Thank you. Any questions?
How do you formalize this second condition of the first result that the so I guess it's like either you have many rounds or you use a group action in a non-black box way, but do you specifically have to evaluate a circuit computing the group action?
You're referring to the interpretation, right? Like these slides?
Yes.
Yeah. So the thing is that our result is proven in the sort of shoot group model. So the idea is that if you don't rely at all on the circuits, then you're allowed to rely on the set element representation, but not on the circuit. The moment you rely not necessarily on the circuit as a whole, like you don't need to use garbled circuits. But if you rely in some way on how the circuit is defined, then you cannot compile anymore in the this version of the shoot action, this group action model.
Thanks.
Thanks for the question.
So the only way to circumvent the lower bound is if you have a circuit that actually computes the group action. That's the only way there, right?
That's the only way I can envision, at least.
Okay.
Okay. Or at least, I mean, I would say informally, it's any way that prevents you to compile the adversary into some other algorithm in the generic action model. Yeah.
I see. Thank you.
Thanks.
Any other questions? All right, let's thank the speaker. We're quite ahead of schedule, but here's our last talk of the session. Algebraic group model with oblivious sampling by Heiger Lipma, Roberto Pericella, Jano Sim, and Roberto will be giving the talk.
Thank you for the introduction. This is a joint work with Helger Lipma and Jano Sim. Okay, we will deal with cryptographic groups. So let me introduce the notation that I use. I will use bracket notation, which means that a group generated by this generator, I indicate the generator with the 1 in bracket, and I indicate a group element with the X in bracket. So particularly the group element of order X with X in bracket. And the group is additive, so the group operation is the addition. And this scalar multiplication that we can see in the slide correspond to the exponentiation. Then we have some hardness in this group. So for instance, discrete logarithm assumption is required to hold, but also other assumptions such as the CDH assumption and this Q power discrete logarithm PDL assumption and many more. Okay, when we want to prove the security of some primitives or assumption in these cryptographic groups, we often require to use strong ideal models to model the group. The most famous one is the GGM, or generic group model, which very roughly speaking, is equivalent to suppose the existence of a perfect unstructured group and to give parties access to an oracle that performs group operation for all parties. But this is a very strong and unrealistic model that suffers from some criticism. Particularly, we know that it's impossible to instantiate generic groups. Of course, proof of security in GGM does not prevent attack against group-specific algorithms. And lastly, and this may seem like a technicality, but it's actually a very important point, a reduction in GGM can always program group element with random known exponent. And actually, many proofs in GGM use and rely on these third features of the model. In order to improve and solve some of these criticisms, in 2018, Fuchs-Bowser et al. Introduced another ideal model for groups, the algebraic group model, or AGM. Here, they give a adversary access to the real group, but they restrict the adversary to be algebraic in the following way. So the adversary receives input in the form of group element, and then output group element, but the adversary, the algebraic adversary, must provide an explanation of the output in terms of a linear representation of the input. So here the adversary output this group element T in bracket, and it also has to output coefficient alpha, gamma, and beta, such that this linear relation between input and output is satisfied. Okay, AGM solves some of the previous criticisms, so capture some known group-specific algorithm, allow us to do proofs by reduction, but it has some own criticism, and it inherits sums, particularly it inherits the uninstantiability result, at least in the most general form. Now recent works point out that the relation between GGM and AGM is somewhat shady. And lastly, this is what we focus on this work. We can use AGM as well as AGM to prove the security of knowledge assumptions that are actually insecure in the standard model. This is because algorithm in the standard model can do this operation of sampling group element without knowing their discrete logarithm. Particularly, say that they pick distribution D with super polynomial mean entropy, then they sample a seed from this distribution, and then they use an encoding function to encode the seed into a group element. If we choose the encoding function wisely, then we can show for some encoding, we can actually prove it, that to compute the discrete logarithm of the random variable induced by evaluating the encoding on D is as hard as computing the standard discrete logarithm. So here we can see that even if we give to an adversary the seed, use it to compute this group element X with the encoding, it is hard to compute the discrete logarithm X. And for instance, there exists a family of functions which is called encodings on elliptic curves that has this property. So at least for elliptic curve groups, this is something real, like real adversary can do these things of sampling a group element without knowing their discrete logarithm. Okay, with this in mind, let me show you this toy example of a knowledge assumption. So we have a challenger that gives the generator to an adversary, and then the adversary sample a group element. We require, by assumption, the existence of an extractor that recover this discrete logarithm X, for instance, because a reduction want to use discrete logarithm. This knowledge assumption trivially holds in AGM and in GGM as well, but due to oblivious sampling, we can see that for what we have seen in the previous slide, that an adversary in the standard model can actually break this knowledge assumption, because if we use these encodings that I've talked before, then under the discrete logarithm, no extractor exists that can compute X. And now you may think that, okay, this is maybe true, but this looks like a very silly knowledge assumption. No one would use it in practice, so why should we care? So let me show you another example. This example is motivated by the Kids AG commitment scheme, which is actually widely used in practice. The challenger now gives a bunch of group elements to the adversary. These group elements are of order sigma, evaluated in various power. And then this adversary output a group element, which we can think of this as the evaluation, as the element of order f of sigma. So the evaluation of a given secret polynomial in this trapdoor sigma. And we require, again, the existence of an extractor, and this time the extractor will recover the coefficient of the secret polynomial used by the adversary. This looks like a more reasonable knowledge assumption. So reasonable that it is actually used in the security proof of concrete snarks constructions such as Plonk and Luna. But once again, this is a knowledge assumption that is secure in AGM and GGM, but due to oblivious sampling, insecure in the standard model. So we actually argue that it's important to have an ideal model for group, which prevent to prove the security of such spurious knowledge assumption. And this is what we did in this work. So we define AGMOS, AGM with oblivious sampling, in the following way. We give an algebraic adversary more power, allowing it access to a non-programmable oracle. The adversary can query the oracle with pair of function and distribution. Then the oracle will sample a seed from the queried function, from the queried distribution. We'll use the querying function to encode the seed into a group element and then return this pair of seed and group element to the adversary. And the adversary now, when compute its output, has to explain the output as a linear representation, not only in terms of its input, but also in terms of the group element returned by the oracle. So for example, here, if it queried for only one element, then this adversary will also output this fourth coefficient delta, which is the coefficient of the queried element returned by the oracle in these linear relations in the slide. And importantly, the model will not allow the reduction to know the discrete logarithm of this Q element, and will not allow actually any party to know this discrete logarithm. Okay, so how can we use this model? Let me show you how can we prove that the CDH assumption is secure in this new model. We have this AGMOS adversary. We give to this adversary a CDH challenge. Then this adversary can perform its computation. At some point, we'll perform some query to the oracle. The oracle responds as we have described before. And eventually, after many queries and computation, this adversary will output a group element, which is supposed to be the CDH, the output. And then it also provides a linear representation of the output. The adversary wins, of course, if it breaks CDH. So if z is equal to x times y, and since the adversary is algebraic, these linear relations should hold. Starting from these two conditions, which define a successful AGMOS adversary, let's proceed with the proof. So we can implicitly define a verification polynomial using formal variables for the variables x, y, and q involved in the games. So this is the verification polynomial. And in case the adversary is successful, then x, y, and q involved in the game will be a root of this verification polynomial. To go on with the proof, we divide the proof into three cases. Case one says that the verification polynomial is actually 0 as a polynomial, and this we can show that this is impossible. Then case two is the case that this verification polynomial is not 0 as a polynomial, but if we evaluated it in x and y, so it's now only a polynomial in the variable that represent the oracle answer, then this second polynomial is 0 as a polynomial. Intuitively, this corresponds to the case where adversary has not used the oracle group element. And we can show that this happens with negligible probability through a reduction to a discrete logarithm style assumption. And the third case, where also this last verification polynomial is not zero as a polynomial, we show that this again happened with negligible probability through a reduction to a new assumption, the Topher assumption that we introduce it in this work. So the introduction of the Topher assumption is actually the main technical part of this work. Let me just explain you what this assumption is. This assumption is parameterized by a family of a function and a family of distribution. And the adversary playing a game where it can interact with the oblivious sampling oracle. And at the end, it has to output a vector. And the adversary wins the game if the vector that it outputs, it's orthogonal to the vector of 1 concatenated to the QIs, which are the discrete logarithm returned by the discrete logarithm of the element returned by the oracle. So basically, these assumptions say that as long as we choose the function of the distribution from these two families, the adversary is not able to use the element returned by the oracle in a meaningful way. Okay, so this is the end of my talks. Thanks for your attention. If you are interested, check the full version of the paper on ePrint, where we have many security proof to show actually that in most cases things are secure in Agimos. And now I will happily take questions.
Yeah, questions?
Did you manage to find any relationships of your new tougher assumptions with like any standard assumptions?
That's a good question. And actually, I add another slide about the cryptanalysis of Topher. Okay, so the answer is no. And because we decided to have the model that is to have the assumption that is general in order to capture the most general model, which implies sampling from non-uniform distribution and any way that we know to have reduction of this to have a reduction for this kind of assumption implies actually sampling the group element with no discrete logarithm, or implies to embed a group element that is given as a challenge in some other group elements without alter the distributions. And this is not clear. It's not clear how to do this in the general case. We have a GGM proof for the new assumption to show that it seems that to require that the distribution have super polynomial mean entropy it looks necessary, meaning that if not, there could be some generic attack to this assumption. But also the GGM used for this proof is not standard because we have to assume some sort of hashing. Yeah, I think this is the most important open problems. One good feature that the model has is that the security proof is independent from the specific Topher assumption that people use. So actually, these two are orthogonal problems. We can study security in Agimos of things, and then we can study like necessary and sufficient condition on the this function epsilon and d, such that the corresponding Topher holds.
Thank you.
Any other questions? All right, let's thank Roberto, and also the other 3 speakers from the session. And we're now off to coffee break.